The first speaker is David Grynkiewicz. He'll be speaking from University of Memphis. His title of his talk is the 3K-4 theorem modulo prime for large density sumsets. David.
All right, well, thank you. Good morning to everyone, good afternoon to everyone, and good evening to everyone. I know these are difficult times, so I'm very grateful to have this invitation to be able to speak here, even though it's less than ideal, given the circumstances. We're making do as best we can. And I actually met Balu only a year ago, and it was in India at a workshop there, a lovely workshop. And that was right before COVID all hit much harder. And it was one of the last workshops or conferences that was able to take place personally. It was just afterwards, I remember flying back and they were just putting in the mask mandates and other stuff. And things hit much harder afterwards. And hopefully things will get much better soon. But we're making do in the meantime. And the topic of this talk is going to be in combinatorial number theory. And it's actually something related to things that happened at that last workshop. So I thought it an appropriate topic for the talk at this celebration here. So let's just start off with some basic notation. So I'm going to be talking about sumsets. And sumsets you may have seen before. We basically have some abelian group, and we're not studying the abelian group. We're looking at subsets A and B of this abelian group, and we define their sum or their sumset to be A plus B, all the little a plus little b with little a and little b and b. And what the type of results that I'm talking about are inverse types of results. So here I put on a slide Feynman's theorem. This is perhaps one of the first inverse results that was sort of proved in this area way back in the middle of the last century. And here's a formulation of it over here. It's been generalized since many other variations, other such theorems as well. But basically, if you had like a set of integers, so here we're considering finite, non-empty subsets. And if it has small sumset, if the size of A plus itself is no more than a constant times the cardinality, then the set has to have structure, right? It has to be contained as a dense subset of a arithmetic progression, well, a multi-dimensional arithmetic progression, which is just a subset of d different arithmetic progressions. And there are universal constants bounding the dimension and the density. Feynman's theorem has gotten a lot of attention. There's lots of important applications of it. I'm going to focus on a special case of Feynman's theorem. So in general, the bounds for Feynman's theorem are still a work in progress. And in general, you have multidimensional progressions. But if the sumset is small enough, then you're guaranteed to not be well contained inside an arbitrary multidimensional progression, but inside an ordinary arithmetic progression. And the bound which guarantees this is this 3K-4 bound. So here we have the statement over here. It was proved by Feynman back in 1959. It says if we have the cardinality of the sumset being, let's say it's R more than the sum of the cardinalities of A plus A, and we're sort of measuring the additive increment from the sum of the cardinalities. And this makes some sense because particularly for the integers, R is always going to be at least -1 because we have a trivial lower bound in the integer case. And we could put a -1 there or not. It's never so clear whether to have R be, so that it's at least 0 or at least -1. But the main thing is that afterwards, we have an upper bound of 3 times the cardinality -4. And to explain the name, in the original work of Feynman, he let K denote the cardinality of A, and the upper bound was 3K-4. That's why it's sometimes called the 3K-4 theorem. And the result is that basically in these circumstances, A is contained inside an arithmetic progression, ordinary progression. And there are exact bounds on the number of holes, the missing elements inside that progression, R plus 1. And this is one of a few examples where we have actual exact bounds on just how well contained A is inside that arithmetic progression. Now there's been many generalizations of this theorem since. Here I put on the next slide one that works for distinct summits. So not just A plus A, but A plus B. And it's going to become important later on for what I'm talking about. And this, well, in various forms, was proved either by Feynman or by Levin-Smilansky or by Stancescu. So it has a bit of a longer history. Feynman has an original paper in Russian, which isn't quite as well known as some of his other papers, proving something close to this, at least partially this. It is all in Russian. Then Leibniz-Milanski gave a variation on this result involving the diameter of the sets. And Francesco later on sort of gave a short little observation that you could prove this result that was more similar to Feynman's result from the version of Leibniz-Milanski. And the statement is basically here we have the same R additive constant above the sum of the cardinalities, and now the 3k minus 4 theorem is more or less the sum of the cardinalities plus the min cardinality minus 4. And in that case, the sets A and B are both well covered by arithmetic progressions with the bounds being tight. And as I said, they're tight. Well, here's an example showing why those bounds are tight. There are, of course, two bounds in the theorem. One is the hypothesis, which is saying that you can't go beyond 3k minus 4. And so over here, if we just took A to be a union of two arithmetic progressions, and we spaced them really far apart, let's say the arithmetic progression with difference 1. Then when we add A to itself, well, we would do a short little calculation, and it would be exactly 3 times the cardinality of A minus 3. And there'd be no way to bound the number of holes because we could keep on pushing the arithmetic progressions further and further apart. And as a small variation, we could take A being the union of those two arithmetic progressions, difference 1, far apart, and B being a single arithmetic progression with difference 1. And if we add them together, we find the sum set of cardinality A plus 2B minus 2. And that's just one off from being an optimal lower bound. And we can slightly modify the statement for distinct summons to sort of take this into account. But in this talk, to avoid those technicalities, I'm not going to deal with that too much. Here's the other bound, right? The bound on how many holes the progression has to have. So I've done it as a little picture over here. So you can imagine the dark dots are supposed to be the elements of the set. And the circles, the open dots, should be the missing elements, the holes inside the set. So we have over here the arithmetic progression, which is well containing the set A of cardinality little a. We have an arithmetic progression, the same difference 1, well containing this set B, and there are the R plus 1 holes inside it. And when you add them together, you get a set that looks more or less the same. And again, there's a long length arithmetic progression at the beginning, sum of the cardinalities minus 1, and then R plus 1 holes afterwards. So this basically shows you can't beat R plus 1 for the number of holes unless we sort of modify the statement of the theorem somehow. And there's an important observation we could about that final sumset set. So what if I took its complement? So here I'm just replacing every dark dot with a white dot. So we're looking at the complement of the sum set inside Z. And of course, since we're inside Z, it stretches out all the way to the left, off to infinity, and all the way to the right to infinity. But you can sometimes imagine, well, what if you sort of loop things around? Z is like a very long line, but it's very typical to sort of loop that line around into a circle. And if you did that, then you sort of have a long length arithmetic progression starting here and zooming all the way off to infinity and back down here, a long length arithmetic progression followed by a portion with a small number of holes, R plus 1 holes. So in some sense, the sum set is also its complement well contained inside an arithmetic progression if you sort of allow it to pass through the point at infinity. This is going to be important. So here's another version. So this was in the symmetric case, A equals B, proved by Feynman, and then sort of updated to the distinct summon case by Barbachy and myself. So we have the same hypothesis of the 3k minus 4 theorem, and I've normalized so that zeros inside both sets. That is, there's no bearing really, except to simplify some notation. And then we have the same conclusions of the 3k minus 4 theorem, except that we gain something else. The sum set has a long length arithmetic progression, at least the sum of the cardinalities minus 1. Just like in that example, that actually shows this bound is tight. And like I mentioned, if you take the complement of the sum set, and I'm going to throw a little negative sign there, though it may or may not be clear why I'm doing this, but you take the complement of the sum set, that's well contained inside the complement of the arithmetic progression. Most R plus 1 holes. These are basically equivalent statements when you do a short calculation. And while R isn't an arithmetic progression inside Z, it's close to being one. And this is this third set that's sort of having a symmetric almost relation as this two other sets A and B, even though it does have infinite cardinality. This complement of A plus B. So that's all the stuff inside the integers. And the title of this talk involves sumsets mod P. So let's move to modulo prime. And there we currently have well, it's conjectured that there should be a version of this 3k minus 4 theorem that holds modulo of prime. And also probably versions modulo non-primes. There's been some recent advances giving results for non-primes too, but this talk is going to focus on the primes, where we've had yet even better balance than what we have currently for the composite case. And the exact statement of the conjecture is probably still a little hazy, but this is probably the best that we can hope for if this conjecture is going to be true. So again, we have a single subset A, which is what I'm focusing on for this talk. It has R more than the sum of the cardinalities. It's at most 3A minus 4. And you'll notice we have a density assumption. The sumset can't be too large because, of course, if it was very close to the entire size of the group, we'd expect the behavior, the similarity between Z mod PZ and the integers to break down. And our best hope was that it would hold all the way up to P minus 4 minus R. So nearly density 1 with a minus R term there afterwards. And of course, the conclusion is that A is well covered by an arithmetic regression. And now the complement of the sumset as well is well covered by an arithmetic regression, which is, of course, equivalent to A plus A containing a long length arithmetic regression. And there's a typo there. There is no B. B is A. I work so often with distinct summons that I sometimes just automatically write a B there. So to explain where that bound P minus R minus 4 is really coming from, let's talk about something that goes back, as far as I know, to Vosper. Maybe earlier instances. I just know that there are references to this in Vosper, at least in some form. And so for here on out, I'm going to use this bar notation to denote the complement of the set, whatever it's barred over. So X bar is the complement of X inside the larger abelian group G, which for us was going to be Z mod PZ in general. But here, this result just holds for any finite abelian group. And then we say we have two pairs of subsets, A and B, and their sum is R more than the sum of the cardinalities. So we're using this R as this additive increment over the size of the original sets. We set C to be our third set, the complement of A plus B negated. And then a very basic observation shows that A plus C is contained inside negative complement B, and B plus C is contained inside negative complement A. And we have these upper bounds that A plus C, it's the size of the set is no more than the sum of the cardinalities of A plus C plus R. And the same thing with B plus C. So that if A plus B has small cardinality with regards to this R, then so will these other two sumsets, A plus C and B plus C. And so in some sense, this pair A plus B is just one pair out of three. And we have actually three sets, A, B, and C, and you can look at any one of those pairs and they all have small sumset and they interact with each other. And this interaction, we can take advantage of it. And we're going to, when we talk about what we're going on in this talk later on, it's going to be how we achieve some of the improved bounds. And the P minus R bound comes from this little observation. If we have the sumset of A plus B being at most P minus R minus 4, well, that's the same thing as saying the cardinality of the third set C is at least R plus 4. And so A plus C is at most A plus C plus R, then it's really A plus 2C minus 4, which is that same bound, that 3K minus 4 bound for distinct summons. So in some sense, this P minus R4 bound is simply saying we have the hypotheses of the 3K minus 4 theorem, not just for A plus A, but also for A plus C, and A, well, in this case, A plus C a second time, because we have A is equal to B. So all the two choices of pairs, two sets of three pairs are going to satisfy the 3K minus 4 bound. And so that's some explanation as to why we might hope this would be the best. And of course, there are examples showing we can't go beyond this bound. Simply taking that like that two-dimensional arithmetic regression and considering it modulo the appropriate prime. So let's talk a little about what we do know about this conjecture when it's true, because there's been a lot of partial progress. And so I'd like to talk a little about some of the cases where we know that the conclusion is true. And in many of these cases, they only talk about the containment by an arithmetic regression. But now that we have the results for the integers that allow this version of the 3K minus 4 theorem that says there's a long length arithmetic progression inside something below the 3K minus 4 bound, that also is enough to guarantee that all those older results that only gave containment, they now automatically also give the second half of the theorem. There's the third set is also well contained. This can all be easily shown. So maybe we should start with the first result of Freiman. here, he was not able to prove the entire conjecture. In fact, there was no conjecture back then. This is the sort of the source of the style of result. And they sometimes call the Feynman 2.4 theorem, although the method yields different constants. But basically the idea is that if you have a stronger small doubling restriction, so it's not at most 3a minus 4, it's now 2.4 times a minus 3. And you have a stronger density restriction. It's not all the way up to p minus that r constant, it's density 0.02. These aren't tiny numbers, but they're not ideal numbers either. They're sort of moderate sized numbers. They're reasonable numbers, not minuscule, but also not ideal. And under these conditions over here, the theorem is true. Originally, it was just the containment by an arithmetic progression, but as I mentioned now, that now implies the long length arithmetic progression as well. So the third set is also long contained. And the methods from this paper over here are going to be important because we're going to use similar methods to what Feynman used in his original 1961 paper. Now, there are other results too. So an observation or some Bilou, Lev, and Rusha, they have a whole paper where they talk about methods of how you can reduce, well, basically from a finite group, say mod p, into the case of the integers. Rectification arguments, as they're sometimes called. If a set is sufficiently small, then in some sense it's isomorphic. It behaves no differently than an integer subset. This can be made very formal. We'll talk a little bit more about it later. But basically, when the set is, say, log p in size, then it's the same thing. It behaves the same way as an integer subset. There's an isomorphism, a Feynman isomorphism between that subset and an integer subset. And then you can apply the results for the integers to study the set. And so we have the result for the integers up to 3k minus 4. So you can apply that result there and then pull it back via the isomorphism to get the result mod p with a bound of log p. So this is, of course, not a density result, but it is some bound that says if a is at least not too big, then the theorem will be true, all the way up to doubling constant 3. So moving back on to, say, improving on what Feynman did, something where we have moderate sizes in the doubling restriction and also on the density. Rodsev basically improved a little on the calculations that Feynman did. Feynman was a little sloppy with some of his Fourier calculations. The main innovations he was using was to use Fourier analysis combined with combinatorics to give this result. And he was maybe not as precise with the calculations for giving the estimates for the Fourier coefficients than Rodsev was. And so just by being a little bit more careful, you can get quite an improvement in the actual calculations. It went from 0.02 to 0.09. And I'll carry on basically with this idea of rectification. We have Green and Rusha who gave a sort of a different one. So the idea that was used in that paper of Bilou, Lev, and Rusha was that, the set was very small, any set, its some set would be guaranteed to be isomorphic to some integers. Here, the idea behind this paper here was to use results that would give, well, depending on the, yes? Was there a question? Okay. Something depending upon the doubling constant. And so here it is small, doubling constant was 3. And so based upon that, they could give something that was a density result, some a times, constant times p. And of course, the constant was very small though. So something like 4 times 10 to the negative 72. So there's a lot of zeros there before we get to the p. But it's a linear bound, a very small linear bound. So this is certainly less than ideal because in many applications, it's important that we be able to consider dense subsets. That widens the range where these results can be applied. And sometimes we really need to apply them for dense sets. So this result gives us a doubling constant all the way up to 3. It's a density result, but it's so tiny that it's not always applicable. Now we can go to the opposite extreme. What if we would try and get the optimal density bound? So we have some nice work of Serra and Seymour. And they got the optimal density bound, p minus r minus 4. But of course, they had to pay a little bit of a cost for that. And they had to weaken that small subset hypothesis from, say, what Feynman had of 2.4 to 2.0001. So it's not minuscule, not like something like 4 times 10 to the negative 72, but it's far from the level of it's far away from being 3 anyways. So there's still work to be improving on that bound there, but it is the optimal density. It's one of the few results that actually would apply in a large density setting. It's been very hard to get results applicable in large density settings, and their result goes up to the conjecture bound. And in a sort of related result there's another result of myself, which you might, when you first look at it, it says, well, you can get doubling constant 3k minus 4. And you can get density p minus r minus 4. So it's basically the whole conjecture, but you have to add one extra restriction. So it's not the whole conjecture. Right? You need r to be dense inside p. So again, and that density bound r has to be no more than some really small constant times p. 3 times 10 to the negative 1549, and just a rough estimate, it's going to be minuscule. So this is of order of the similar stuff as to what's coming out of the Green and Roosh arguments. But at least we get both at the same time, and it's saying that at least for a sufficiently large p, comparison to how much we're incrementing over the size of a plus a, the theorem will be true. So there is some evidence, some hope anyways, that the full conjecture might be true, and although we're still working on how dense we can make the sets. So we could talk a little bit about that density bound, because that density bound depends upon that additive increment r. And so that you have p minus r. What if you wanted a bound that didn't depend upon r? So I mean, here we have the hypotheses we have. Let's write r as being some constant alpha times the cardinality minus 4. And so then, since we have this bound being 2a minus r being at most 3a minus 4, that's equivalent to saying a is between at most 1. And it's going to be at least 0 because it's always at least negative 1. Because we have the Cauchy-Davenport there, if you're familiar with it. But r is going to have a similar lower bound as you have for z. And if you did a short calculation, you'd see that this popped out of it. So I've done the calculation up here, but you can jump right to the end if you rather. The sum set has this sort of density 2 alpha divided by 2 times 1 plus alpha times p plus 4, and then the whole thing minus 4. But it's basically a density 2 plus alpha times 2 over 1 plus alpha. And you could ask, well, if you want a bound that's independent of r, so they're independent of this doubling constant, it works for all sets inside the range applicable for the 3k minus 4 theorem. Well, what will be the smallest this upper bound could be? And a short calculation shows alpha equals 1, where you have density basically at 3a minus 4. And there it becomes 3/4 p. So in a weak sense anyways, 3/4 p is the optimal density for the prime and 3k minus 4 theorem modulo of prime. I mean, obviously we still expect to get something more like density p minus that constant r. But if we want something that's applicable, a uniform bound for all possible doubling constants inside this range, then we wouldn't be able to beat 3/4 p. And so we're going to talk about the rest of this little talk here, what we can do under these density assumptions. And prior to our work over here, the only result that would be applicable in this range was the result of Uriel, Serra, and Zimor. And so that was this one that went up to the optimal density of p minus r minus 4. And it had a doubling constant, basically 2 plus 0.0001. So it's at least something, not minuscule, but still pretty small. We wanted to improve that. And here's the improvement we were able to manage. So again, we have here now the same hypotheses as the 3k minus 4 theorem mod p. And you can see we have the density restriction as being 3/4 p. So that's up to this semi-optimal, this rough approximation of the optimal density. And our restriction is going to be a small sumset hypothesis of about 2.1368. So, in comparison to 2.00001, this is a lot better. It's getting closer to that sort of like 2.4 level that we had from Feynman's original result, a little bit less, but we have much higher density. And the conclusion, again, is we get the desired conclusion. A is well covered by an arithmetic regression, tight bounds, and of course, by the current machinery, that automatically implies that the third set, the negative of the complement of, again, that should be a plus a, is well covered by an arithmetic regression as well. Same bounds. So let's talk a little bit about how we got this improvement. So one of the key ideas was we're going to follow the general approach anyways of Freiman, back from that paper in around 1960, 1961. And so the idea of that paper was, well, to use Fourier analysis. And using Fourier calculations and putting the points on the circle, was able to show that, if, given that hypothesis about having small sumset, that forced there to be a large subsumset, some A plus B contained inside A plus A. So A prime is inside A and B prime is inside A. I didn't sort of write that down formally, but that's the case. So we have a large subsumset contained inside A plus A. And it's isomorphic to an integer subset. So, I talked about this informally before. One way we can really have a simple isomorphism is say A is contained inside a short length arithmetic progression, A prime and B prime as well. So let's say we have A contained inside some interval, of difference 1, or say difference D, and length, P minus 1 over 2. And the same thing for B prime. Right, so we basically start at x plus 0, then d, 2d up to p minus 1 over 2, and the same thing for b. And if we were to add a plus b, that whole set is going to live between x plus y, and then plus 0, plus d, plus 2d, all the way up to, well, p minus 1. So we're never actually looping around inside mod p. Right? We don't have to use the fact that p is equal to 0 modulo p. Addition in this setting over here is going to basically be the same as if we had added with just ordinary integers. And so in that sense, we can simply lift these sets directly up to the integers and just apply the results for the integers, get the results there, and then push them right back down. And they're going to hold in the original set Z mod PZ with respect to this difference. And of course, we have to have some difference D because unlike the sort of canonical differences for the Z, we have 1 and -1. For mod PZ, well, we have any non-zero difference is going to give us an arithmetic progression that covers the whole group. And so the Fourier arguments basically get A prime and B prime contained inside short length arithmetic progressions. Progressions that have length at most half the order of the group. And we can't get the entire set of A inside the short arithmetic progression, but we get a large subset. And that's sort of the start, the kernel of the argument, right? And of course, we're going to use the better estimates of Rodseth for doing those Fourier calculations so that we don't lose any loss there. And then afterwards, that's when the combinatorics takes over. So all the more discrete arguments. So we're going to consider a subsumset A prime plus B prime contained inside A plus A. And it should be isomorphic to an integer sumset. So it's well contained inside these short length arithmetic progressions of say length no more than P over 2. And we want to consider one that has the sum of the cardinalities A prime plus B prime being maximal. So of course, since we have a large such one by this Fourier analysis approach, well, we can consider one that's maximal and it will also be large. And just because the notation is symmetric, we can assume that B prime is the smaller of the two cardinalities. Now, I should mention that inside the original work of Freiman, B prime was always equal to A prime. And so here we're doing a slight variation. We're actually allowing the two sets to be different to give us some more flexibility. And this is actually going to help us improve the constants by having this extra flexibility. So it may not be immediately evident why I was starting off from even from the symmetric case when A is equal to, when B is equal to A, we're adding A to itself. Why passing to two distinct sets can actually give us better constants, but it does. It allows us some flexibility to move around, and we're going to incorporate that third set. And well, let's talk about what we do with this bound. So the basic idea of Freiman was that we don't have the optimal small sumset hypothesis for A plus A. Instead, we have some hypothesis that, in our case here, it's at most 2.1368 times the cardinality minus 4. Oh, I think it should be minus 3, but regardless. So we get something that's, A has a strong or small sumset hypothesis. Now, A prime plus B prime is contained inside A plus A. So we have this trivial upper bound. It's no more in size than the sum of A plus A. I mean, ideally, we would expect it to have much smaller size. But it's kind of hard to show that right from the start. If we could do that, we could actually improve the calculations a little, but even though we would certainly expect this, to show this is harder. So we have this trivial bound. Because it's much smaller than the 3k minus 4 bound, if we actually go into the details of how much smaller, out pops the 3k minus 4 bound for A prime and B prime, what we get for distinct summons. And so, of course, you have to do a calculation, and it's exact what comes out of those forward calculations that gives the right amounts that, with regards to the small sum set, they interact with each other. So there's a lot of calculations going on to get the numbers to work out. But when everything is chosen appropriately, out pops the hypothesis we get to apply the 3k minus 4 theorem in Z to A prime plus B prime. And remember, they're isomorphic to an integer sum set. So we're allowed to do this. We can take the isomorphic copy, apply the result for the integers, get the structure for the isomorphic copy of A prime plus B prime, and then pull that back to the actual A prime plus B prime via the isomorphism. And the isomorphism is very simple. We're just basically, if this is our set there, where 0 is going to 0, D is going to 1, and so on. And the 3k minus 4 theorem tells us that A prime and B prime are well contained inside an arithmetic progression. And in this case, it would be one with difference 1. And so that would translate to that arithmetic progression with difference D that we started with. A prime and B prime were both contained in one that was short, no more than half the size of the group. Well, now it's much smaller. It's something that depends upon the doubling constant. And so we shrink that interval drastically. So we have now A prime and B prime contained in even shorter intervals. Say x plus, 0 to m, but it could be, if we translate things appropriately, contained inside that original interval, 0 to p over 2. Although we may have to translate the intervals. Doesn't matter. Let's keep things simple. So if we actually had A prime and B prime both being equal to A, we'd be done. Right? Because then we'd have the entire set A itself well covered by an arithmetic progression. And then that would also give us the corresponding result for the complement by the result in Z as well. So there has to be some element that's missing, something that's not inside A prime or something that's not inside B prime. It's an element of A that's not contained inside that interval from 0 to m, or from 0 to n. Now, Z has to be kind of far away from the endpoints of that interval, because if Z was inside an interval of length p over 2 that included that interval from 0 to m, well, we could add Z to A prime. And we still have a subset, a larger one than A prime, that contained all of the previous set of elements of A prime plus one new element, all inside an arithmetic progression of difference D and length at most 1/2 of P. It would rectify. It would be isomorphic to an integer sum set, and we would contradict the maximality of A prime and B prime. Well, that can't happen. Z has to be kind of far away from the endpoints of 0 and m, and also 0 and n. And it turns out that if we had a density assumption about P over 2, so 1/2, then being far away from the endpoints would easily be able to show that the difference in cardinalities between A plus A and A prime plus B prime was big enough. We'd make up for that difference, and we get a contradiction right away. And we gain lots of new elements. It would be much bigger than A prime plus B prime, and it would just be too large for our hypothesis. So the complete proof would end right away, and we'd be done. The problem is, of course, these simple arguments for density 1/2 break down at 1/2. So we need something new, something to push it beyond 1/2 to get closer to 3/4. That's what we're going to do. So we need a new trick, something to get better, because we need to, pass up from 1/2 to 3/4, where we need to go basically 50% further. So we need something else that's going to give us that distance. And surprisingly, we're not going to need. We're going to just need some simple little combinatorial stuff involving that observation of phosphor from back in the middle of the previous century. So we'll start off with a calculation. I'm not going to give the calculation, but a short little calculation using some of those results from phosphor shows that if we add A prime to the third set, so minus A prime plus A complement, it satisfies the 3k minus 4 hypothesis. Now, of course, these are subsets of Z mod PZ, so we're not guaranteed we can apply the 3k minus 4 theorem to these sets, but if we could, they certainly satisfy the bound that would be necessary to do it. So this is a good start. And of course, since A prime plus B prime is contained inside A prime plus A, remember B prime is contained inside A, we could take their complements, and that swaps the order. That means negative A prime plus A complement is contained inside negative A prime plus B prime complement. So when we take a complement, the order of inclusion swaps. And we notice that that A prime plus B prime complement, that's the third set inside the 3K minus 4 theorem for that integer subset, A prime plus B prime. That's something that's isomorphic to the integers. That third set is available in the integers. It's the sort of the missing one, which contains, if we took its complement, a long length arithmetic progression, or when we take its complement, so this third set, it's also well contained inside an arithmetic progression. It's contained inside a short arithmetic progression. And so A prime plus A complement is also contained inside a short length arithmetic progression because we have this inequality here. So if the third set from our integer subset is well contained inside an arithmetic progression, then this set is too. Well, that's nice. We do another calculation. Now it turns out it's small enough. The length of that progression is small enough to guarantee that A prime plus negative A prime plus B complement, right, that's also going to rectify. That's isomorphic to an integer subset. So they're both A prime, the interval length containing A prime and the interval containing this set over here, they're small enough that we never overlap past P. We don't have to use the fact that P equals 0. It's an integer subset. It obeys the 3K minus 4 theorem by the calculation at the beginning. And so we can apply the 3K minus 4 theorem now to this set, A prime plus the negative of A prime plus A complement. And this inclusion here, that's that observation of a Vosper from the middle of last century. This is all contained inside negative A complement. Because if we sort of did this around, this is A prime plus A. That's the third set for that trio. So what we do, we apply the 3K minus 4 theorem to A prime plus this third set, negative A prime plus A complement. And we use that result of Bardakhi and myself, that there's a long length arithmetic progression inside there, inside the integers. So P is contained inside there and therefore contained inside negative A complement too. This is all via the isomorphisms going on in the background. We take complements and we get A contained inside a negative P complement. Now P is a long length arithmetic progression, so the complement of P modulo P is going to be a short length arithmetic progression. Right. We do another calculation. It turns out it's short enough to guarantee that A prime plus A rectifies, that it's isomorphic to an integer subset. This is nice. So this would actually give us a contradiction right away because we're assuming that A prime plus B prime was the maximal of such set that did this, that would be isomorphic to integers inside A plus A. So the only way we don't get a contradiction is if B prime equals A. But B prime is the smaller set, right? So if B prime equals A, then A prime equals A. And the only way we don't get the contradiction to the maximality of our rectifiable subsum set A prime plus B prime is if A prime equals B prime equals A. And so the entire sum set rectifies. It's isomorphic to the integers and therefore reduces directly down to the integer case where we have those results available to us. So that's the basic idea of the proof and how we were able to sort of leverage that observation in this trio set, flipping back and forth to push and to actually circumvent the density restriction 1/2, to actually extend that argument and get it to 3/4. And in the remaining time that I sort of have in this talk, I'd like to talk about some applications of this result. So the result itself is quite nice, I think, anyways, in and of its own right, but we gave a few short, simple examples, some things to show what you could do with the result afterwards. And so one of the ones I want to talk about, which is kind of what led me to talk about this particular topic at this conference, is something involving sum free sets. So let's just say we have a subset A of an abelian group. It's said to be sum free if, when we take it, sum set A plus A is disjoint from A. So there's no element inside A that can be written as the sum of two other elements of A. So it's sum free. And these are very old, well-studied sets going back to Shor, studied a lot by Erdish and others since. They're a very popular topic. And here's an example of a sum-free set. We could take, say, the middle third interval mod P. So say everything from P plus 1/3 to 2P minus 1/3. We'll assume P has the right congruence mod 3 for this to work out. And if we look at A plus A, then, well, we have an interval summed with itself, so we get a longer length interval. It's everything from 2P plus 2/3 to 4P minus 2/3. And since we're in mod P, that loops around. We get basically everything from 2p plus 2 over 3 to p, and then that's 0. And we go all the way up to p minus 2. But you notice that we never hit the middle third of the interval when we do this. Right? P minus 2 is just shy of p plus 1 over 3. So the a plus a is disjoint from a, and we get an example of a sum-free set of cardinality p plus 1 over 3, basically density 1/3. Right, so this, it's a large density sum-free set mod p. Now you could ask, well, could you do better than this? The answer is no, because we do have this this lower bound mod p. If we have a set which doesn't equal the entire group modulo p, well, then we have the Cauchy-Davenport bound. It says the size of a plus a is at least 2 times the cardinality minus 1. Just like for the integers. And so if a is sum free, then of course a plus a is disjoint from a. So the sum of the cardinalities of a plus a and a is no more than all the elements inside the group, no more than p. Maybe that won't even be possible. It is possible, for instance, in this example here. When we get this trivial upper bound, we apply the Cauchy-Davenport theorem to estimate the a plus a from the below, and we get 3a minus 3. And so that rearranges to saying a has size at most p plus 1 over 3. That's, so density 1/3 is really optimal. So just like we can ask for structural results for some sets, we could ask for structural results for some free sets too. Why not? We know there's an optimal density, a maximal density that a sum free set can have mod p. So what do the sets look like that are close to that optimal density? So this was a question that was actually, I think, first looked at by Lev. And then it was later improved by Desnoyers and Freiman. And then Lev and Desnoyers got together and proved an even better constant. So what it basically says is that if we have a dense subset of A, so we're not quite at optimal, the maximal density 0.3333, we're a little below that, 0.318 times P. And if some A is sum free, then it can't be an arbitrary set. It has to have some kind of structure. And the structure is that it's a dilate of not the middle third interval, but we're allowed to stretch the interval a little bit more as the size of A changes and gets smaller. So it's say the cardinality of A to P minus A, and we dilate it by D. That's A is contained somewhere inside there. It's a larger length middle interval. And of course, we have to dilate by D because we have not only arithmetic progressions with difference 1, but those with difference 2, 3, 4, up to P minus 1, which all are symmetric inside the Z mod PZ. So we could take the middle portion of any one of those intervals with difference, whatever it might be, any non-zero difference. And I'm using D dot X to represent the dilation of X. So D times X, so it's, we take any element of X, little x inside big X, and multiply by D. We're just dilating. So like I said, this has been this was sort of the result of a sequence of various other improvements in the bounds. And you could use our result fairly straightforwardly to get a little bit of an improvement there. So we can improve the bounds that were given by Desnoyers and Lev, and we can improve that from this 0.318 to 0.313. And like I said, this is what motivated me a little to talk about this, because at this conference in India, just over a year ago, right before all Corona hit and everything, we were just wrapping up this paper, myself and Pablo and Gonzalo Sanchez is one of his students. And we were doing the final revisions before it was going to be published. And there was a talk at the conference too, involving this concept of these inverse results for sum free sets, where they were talking about this older result of Desnoyers and Lev, and also about some work that was in progress. So it's even possible that this bound that I put it up here has been improved since then. I checked to see if I could find a paper online, because I think they were currently working on this project in the meet. So I don't know, it may not be finished yet, but there may be some even some better notes afterwards where this bound of 0.313 can be improved even more afterwards. But in comparison to what was currently published, we were able to improve it from 0.318 to 0.313. And so we were kind of happy with that. It was a nice, simple application. And it was basically just directly applying our result, because once you have this high density result, that gives you a strong, an upper bound using, so we don't have Cauchy-Davenport, but we have our result instead. And you get the structure there and can apply the long length arithmetic progression we get inside Z to basically turn it into that long length interval right there. So the details here follow pretty straightforwardly afterwards. We also gave a different application of this. It's sort of a variation. So we have something called an M sum free set. So now we define a set to be M sum free. M is just some integer that's at least 1. If the sum set A plus B is disjoint from the m-fold dilation of A. So you can't write any m times something in A as a sum of two other elements. So of course, if m is equal to 1, this corresponds to being sum free. And you could ask, well, let's set down here this dm of z mod pz to be the maximal density of a m sum free set mod p. Right, so if we do this over here, then basically, and we let p get really large, see what happens for larger and larger primes. This density for the one case, the sum free case, that's 1/3. It's that simple observation where you just write down the lower bound construction. We have the Cauchy-Davenport bound, done. And if you went on to 2, well, then actually this condition about being m sum free or 2 sum free, you're trying to avoid 2-term arithmetic progressions. And that's hard to do for positive density sets. So the density goes to 0 in this case. Kind of a more deeper result involving, arithmetic progressions. So let's set dm to be maybe the limit what this density is approaching for m at least 3. We get some estimates for dm. So that was kind of some of the motivation that was actually my two co-authors were very much interested in. And we were able to use this result to get some improvements here. So for instance, they had previously used that result of Uriel, Serra, and Zimor to give an improvement on this constant dm in the past. But it was 2.0001. It was pretty small. So the constant wasn't quite as ideal as they liked. And it was actually at another conference in Shanghai where I met Pablo. And he was talking about the result they had with the constant, the result of Uriel and Zimor, and how they were able to use this to get some better bounds for the m sum free case. And he was like, if they could only get some better balance for the 3k minus 4 theorem, they would be able to improve the constant much better than what they could manage there. So I thought, well, perhaps we could. And that's where things started. And they later finished up at a different conference in India just last year. And like I said, if you use the same Cauchy-Davenport argument, you get a trivial upper bound or a very basic upper bound of 1/3, but it's going to be less. So here are the bounds that we could come up with. So regarding the lower bound, right, we're going to get more than 0. 0 is 2. The case of 2 is kind of unusual because it's in some sense translation invariant, and things for that behave differently. Once we get back to 3, you can get a bound of 1/8. Now this lower bound is actually a construction of Thomas Shin, or at least he had told Pablo about such a construction, and he had nothing to do with it. So he graciously let us include it in the paper with his crediting him for it. And then the referee took a look at Sharon's construction and thought it could be improved a little, and gave a suggestion for how to improve it. And we took a look at the referee's suggestion and realized that, well, it nearly worked, but there were a few little technicalities with what they had suggested. And with a little bit of effort, we were able to modify the idea of the referee, combine it with the idea of Shern, and we were able to iron out that lower bound. This is all just really fine nuances here to get that 1/8. And still the crux of it is going back to Shern. And so we get a lower bound of 1/8 holding for any n. Whether it's tight or not, there's some, we can get some for smaller values and some slight differences there. But the upper bound was then the main crux, the main sort of application of our result. And before, when they had that result of Freimer, Uriel and Zimor, they could get something over 1.3.0001, it still beats the trivial bound or the basic bound of 1/3 you get from Cauchy-Davenport, but it was very close to 1/3. And so we're still kind of a long ways off from 1/8, but using our result, we can still push it away from 1/3. And we manage 1/1.3.1955. And it's not actually directly using the result I stated in this lecture, because remember that had a density 3/4. The density bound that we basically need for applying it in this question over here is around 1/3. So basically 1/3 plus r divided by 3 or something like that, as I recall. And so we can simply weaken the density restriction a little and modify the calculations, and we get a more relaxed small Sunset hypothesis. Instead of having that 3.14, we get it to 3.1955 instead. So that's where that number is coming from there. It's because we don't need that full power of the 3/4 density. We can actually restrict the density a little And when we strengthen the density hypothesis, we can relax the small sum set hypothesis in sort of as a tug back between the two of them. And that's what comes out of this over here. And so that's all I really wanted to talk about, coming towards the end of the presentation here. So thank you again for letting me talk here. Happy birthday. And I'll be happy to answer any questions in the meantime, although I do have to give a test not too much longer after here, but I'm free for the time being. So that's all.